Module D, Nonparametric Multiple Testing Procedures, Part 2. We are now ready to discuss a class of multiple testing procedures, which serves as a complement of the class that we discussed in Module C. As you remember, in Module C, we focused on multiplicity problems without a fixed, clinically meaningful hypothesis ordering or testing sequence, and as a result, we had to resort to procedures with a data-driven testing sequence. In this module, by contrast, I will introduce stepwise procedures with a fixed or a pre-specified testing sequence. This class includes, as you see on the slide, the fixed sequence procedure, the fallback procedure, and finally a class of chain procedures, also known as graphical procedures. Section D1, stepwise procedures with a pre-specified testing sequence. This is the only section included in this module. And before we get started, it will be very helpful to define the setting, the multiplicity problem that we're dealing with, and summarize the assumptions associated with this setting. First of all, in this class of multiplicity problems, we assume that there is no prior information on the joint distribution of the hypothesis test statistics. This is what defines distributional relationships and forces us to consider the general class of nonparametric procedures. Secondly, when it comes to logical relationships, suppose that the null hypotheses of no effect in our multiplicity problem are arranged in a certain meaningful way. For example, this pre-specified arrangement reflects clinical importance of the hypothesis. For example, the very first hypothesis in the sequence is the most important one, followed by less important hypothesis. Or there could be another scenario. The hypotheses are ordered in terms of the expected probability of success for the associated objectives. For example, the hypothesis could be arranged in terms of the true effect size. Of course, not the expected effect size. The first hypothesis is associated with the largest expected effect size and gives us the highest marginal power, and then the expected effect size is going to decrease as we progress through this predefined sequence. Fixed sequence procedure. This is the most basic example of a stepwise procedure with a predefined testing sequence. It is commonly used in clinical trial applications and almost matches the bond-forming procedure in terms of its popularity because it is based on a very straightforward set of decision rules. But, and there's a very important but here, even though it is popular, it is not necessarily an optimal procedure, and we will discuss in a lot more detail what this procedure entails. But let us first define the fixed sequence procedure. The fixed sequence procedure is based on a sequentially rejective method, which means that the procedure begins with the first hypothesis in the pre-specified sequence, for example H1, and the hypotheses on the slide are, as we have done before so many times, are represented by orange boxes. The first hypothesis in the sequence H1 is located at the left end of the sequence, and then beginning with this hypothesis, the other hypotheses are tested sequentially as long as the procedure continues to reject null hypothesis. Specifically, as we see on the slide, each hypothesis is tested at the alpha level, and testing continues as long as significant results are observed. And as you can see, there's really no multiplicity adjustment at each step, which is great, but the price we have to pay for this is that we must stop testing after the very first non-significant outcome. For example, if the hypothesis H2 is not rejected, the remaining null hypotheses are automatically accepted, even though the associated p-values may be highly significant. That's what we call the single strike rule compared to a 3-strike rule in baseball. A single strike and we are immediately out. This slide gives a formal definition of the testing algorithm used in the fixed sequence procedure. As I said on slide 7, testing begins with the first hypothesis in the sequence, which is H1. Please, I would like to point out that we're not using the parenthetical notation anymore. This is the first hypothesis in the pre-specified sequence. This is not the hypothesis that corresponds to the smallest or the largest p-value. And this hypothesis is tested at the full alpha level, and there is no explicit multiplicity adjustment simply because the hypotheses are to be tested using the sequentially rejective testing algorithm. And at each step, the corresponding hypothesis is rejected if its p-value is less than or equal to alpha, and in addition to that, all of the p-values that are placed earlier in the sequence were also significant. I think it would be helpful to go over the following quick exercise to help us understand the underlying decision rules, and I refer to the rules used in the fixed sequence procedure. What if we try, hypothetically, to apply the fixed sequence procedure to a multiplicity problem that arises in a group sequential clinical trial with 3 data looks? The first look is the first interim analysis. It is represented by the orange box on the left. It's followed by the second interim analysis, and finally on the right we see this orange box that corresponds to the final analysis at the very end of the trial. We have therefore 3 different null hypotheses of no effect to test at each of those data looks, and those 3 hypotheses are naturally ordered because they're tested sequentially, beginning with the null hypothesis at the first interim analysis. Since the testing sequence is fixed, the question is here, can we use the fixed sequence procedure and perform each analysis at the full alpha level? Why do we have to define complicated alpha spanning functions that are commonly used in group sequential trials? Well, of course, it's a kind of a tricky question. As you could have guessed, it would have been great to be able to perform those analyses sequentially, each at the full alpha level, without any multiplicity adjustment, but unfortunately, the answer to this question is no. Because to be able to protect the overall alpha, the family-wise error rate, the fixed sequence procedure must be applied in a sequentially rejective fashion. I've used this phrase several times already. And this phrase means that if we cannot reject a null hypothesis, there's going to be no more testing after that point. But in the context of group sequential clinical trials, this approach would not make any clinical sense, because if we reject the null hypothesis of no effect at an interim analysis, there's really no need to continue. The sponsor has already has enough evidence to claim that the treatment is effective. And therefore, the goals of multiplicity adjustment in the context of a group sequential trial are different from the goals that arise in clinical trials where the fixed sequence procedure is typically applied. As a quick illustration, we're going to apply the fixed sequence procedure to the type 2 diabetes trial. That's example 4. And in this case, as we've said before in module C, there are 3 doses compared to control, to placebo. And here we're going to assume that the null hypotheses for those 3 dose placebo comparisons are ordered before the trial starts. The testing sequence is fixed. Testing begins with dose 1, which is the highest dose in this clinical trial. And the table lists here the one-sided p-values for the 3 tests under scenario 1. We introduced this scenario in module C. And this scenario serves as an example of a favorable configuration for the fixed sequence procedure because, as we can see, there's evidence of a significant treatment effect at doses 1 and 2, the high dose and the medium dose. And as a result, as we see in this plot on slide 11, When we begin applying the fixed sequence procedure in a sequentially rejective fashion, we can see immediately that the first p-value in the sequence, p1, is significant at the alpha level, and here we're using again a one-sided alpha of 0.025. Therefore, h1 is rejected. The fixed sequence procedure then proceeds to the next hypothesis in the sequence, which is h2. This hypothesis is also rejected because p2 is below the alpha threshold. And then when we finally get to the last hypothesis, h3, and when it is tested, it cannot be rejected because we see that the orange dot that represents the p-value for that hypothesis, it is above the alpha threshold. This slide provides a summary of the key properties of the fixed sequence procedure. First of all, this procedure controls the family-wise error rate for any joint distribution of hypothesis test statistics, and that should come as no surprise because it's a non-parametric. That's a Bonferroni based procedure, and those procedures are known to provide alpha control for any configuration, any distribution of p-values or test statistics. And so theoretically they could be used anytime and anywhere, not to suggest that this particular procedure should be used very often, and we'll talk about this a little bit later. But very briefly, to understand why the family-wise error rate is protected when we apply the fixed sequence procedure, let us recall that for each hypothesis, testing is conditional upon rejecting all the hypotheses that were placed earlier in the sequence. So what happens here is that every time we test a null hypothesis, we apply the full alpha level. We, so to speak, invest all of our alpha. And if the hypothesis is rejected, our return on the investment is the alpha. And therefore that alpha can then be reinvested again in the sense that we can transfer that alpha to the next hypothesis in the sequence. But on the other hand, if we fail to reject a certain hypothesis, we lose the investment. There is nothing to carry over to the next hypothesis, and this is why we must stop after a hypothesis is accepted. And regarding power, the fixed sequence procedure performs very well, as we saw in an example that I presented just a minute ago, and its power is maximized provided the monotonistic condition is met. And what do I mean by this monotonistic condition? It simply means that the null hypotheses are ordered from the largest effect size to the smallest effect size. But if a test in the middle of the sequence has a small effect size, it will be underpowered, and then power for the remaining tests is going to drop. There's going to be a good chance that the procedure will stop early before reaching the end of the sequence, and therefore it is very important to verify the monotonicity condition is met before the fixed sequence procedure is applied or is predefined for a given multiplicity problem. Here we see a simple example. We're going to label it scenario 3 for the type 2 diabetes trial, and this example is going to be used to illustrate the importance of this monotonicity condition. What if in the type 2 diabetes trial, the effect size for the first dose, this is the high dose, dose 1, what if the effect size for that dose turns out to be smaller than anticipated? How is this going to impact the other dose placebo tests? Let us assume that there is no significant effect at dose 1. The associated one-sided p-value, as you can see on the slide, is 0.0291. It's slightly above the alpha threshold of 0.025. And let's see how this is going to affect the testing algorithm used in the fixed sequence procedure. In this case, as we can see on slide 14, the fixed sequence procedure cannot reject any null hypothesis, even though there is clearly evidence of a significant effect at doses 2 and 3, but this is before a multiplicity adjustment, of course. When the fixed sequence adjustment is applied, we realize immediately that the first p-value in the sequence is not significant, and therefore no more testing can be done after this point. Because of the single strike rule, the sponsor cannot evaluate the efficacy of this novel treatment at the other two doses without inflating the family-wise error rate, and this is why the monotonicity condition is critical for the fixed sequence procedure. And to help us quantify the impact of underpowered tests on the power of the overall procedure, the overall fixed sequence procedure, and also to help us understand how robust this procedure is, I'm going to present the results of a simple simulation study. We're going to consider a clinical trial with 3 ordered endpoints, and they will be tested. Those endpoint tests will be carried out using the fixed sequence procedure, beginning with endpoint 1 at a one-sided alpha of 0.025. In this simulation study, the endpoints are assumed to be continuous, and they follow a trivariate normal distribution with a compound symmetric correlation matrix, which means that we here assume a common correlation coefficient. The study is set up in such a way that marginal power for each univariate endpoint is exactly 80%, and which means that all individual endpoint tests are adequately powered when we assume that the true effect size for each endpoint is 0.4. We're going to consider 3 different cases, 3 different scenarios. In case 1, all endpoints are powered at 80%, and the other 2 cases are introduced to help us understand what happens if the effect size for the first endpoint is less than 0.04, which means that it's underpowered, or if it's greater than 0.4, which means it's overpowered. Specifically in case 2, the first endpoint is underpowered, the effect size is down to 0.3, and marginal power for this endpoint as a result drops to 55%. And in case 3, the first endpoint is overpowered, the true effect size is now 0.5, which brings marginal power for that endpoint test to 94%. Let us see now how this affects power for the other endpoint tests if we apply the fixed sequence procedure. The summary of simulation results is presented on slide 17. I know there's a lot of information in this table, and I'm going to walk you through it. In general, this table lists the probabilities of rejecting the 3 individual null hypotheses of no effect that are based on the individual endpoint tests. And this evaluation was done under the 3 cases, the 3 scenarios that we defined on slide 16. We're going to begin with case 1. In this case, the first endpoint is adequately powered, but then power decreases fairly quickly as we go down the sequence. When the endpoints are strongly correlated, which corresponds to the case when the common correlation coefficient is 0.5, then power for the last endpoint drops to 61%, even though before this multiplicity adjustment, if you remember, marginal power for each individual endpoint test was 80%. So in the case of independent endpoints, the results are clearly worse. When we assume that the common correlation coefficient is 0, then power after the multiplicity adjustment for the last endpoint is 51%. We went down from 80%, the original marginal power before the multiplicity adjustment was reduced by almost 30 percentage points, down to 51%. Now, considering case 2, this is an example of a configuration of effect sizes where the monotonicity condition is violated. And why is that? This is because the first test is underpowered, which leads to a domino effect, so to speak. The probabilities of rejection for the second and third hypothesis decrease at an exponential rate. And you can see here that as a result of this lack of failure to meet the monotonicity condition, marginal power for the second and third endpoints are below 50%, even though the endpoints were originally powered at 80%. It's of course a dramatic loss of power, and that is true for both correlation scenarios, when the common correlation coefficient is 0 or the common correlation coefficient is 0.5. And finally, with case 3, we see here that when the monotonicity condition is met, because the first endpoint is overpowered, the fixed sequence procedure performs actually quite well. There's only a bit of power loss for the second endpoint. It drops from 80% to 75% or to 77%, depending on the common correlation coefficient. And even in this favorable configuration, the probability of rejecting the third hypothesis is down by almost 20% in the case of independent endpoints. It goes down from 80% down to 60%. The conclusion at the end of the day is that the fixed sequence procedure is not robust. It is in fact quite sensitive to the effect sizes of the tests placed at the beginning of the predefined sequence, and therefore it makes sense, whenever this information is available, it makes sense to apply this multiple testing procedure only if there is strong prior information, strong historical data indicating that the magnitude of the treatment effect is expected to change monotonically across the testing sequence. And when this monotonicity assumption is not met, the fixed sequence testing approach, as we see on the slide, is likely to become quite unreliable. The key properties of the fixed sequence testing approach that we have discussed in this section are recognized in both FDA and EMA guidelines on multiplicity in clinical trials. For example, when we look at the EMA guidance, specifically at section 5.1, it considers the following setting: 2 or more endpoints ranked according to clinical relevance. No numerical adjustment of each single hypothesis test is necessary. However, no confirmatory claims can be based on endpoints that have a rank lower than or equal to that variable whose null hypothesis was the first that could not be rejected. What is important for us to remember here is that no confirmatory claims can be pursued for the tests that turn out to be significant but are placed after a non-significant test, according to a prospectively defined testing sequence. This wording applies to a very broad class of multiplicity problems in clinical trials. For example, to trials with multiple doses of an experimental treatment that are tested versus the control. If testing begins with the highest dose, and that one, for some reason, perhaps due to tolerability reasons, it is not significantly different from the control, then testing must stop. Another example is clinical trials with 1 or more predefined populations of patients. Again, those populations may be tested sequentially using the fixed sequence approach, but the trial sponsor may not make any confirmatory claims based on populations in case there is no significant effect on the population with a higher rank that were placed earlier in the testing sequence that was examined earlier than the current population. This conclusion is fully consistent with the statement or recommendation made in the EMA guidance document. Along the same line, the FDA guidance presents the following warning when it comes to the fixed sequence procedure. Carefully selecting the ordering of the tests of hypothesis is essential. A test early in the sequence that fails to show statistical significance will render the remainder of the endpoints not statistically significant. It is often not possible to determine a priori the best order for testing, and there are other methods for addressing the multiplicity problem. And also a similar statement is found in section 4 of the FDA's draft guidance. it is stated in this section that although it may seem counterintuitive to ignore such an apparently strong result, to allow a conclusion of drug effectiveness based on a second endpoint, would in fact be ignoring the first endpoint's result and returning to the situation of having multiple separate opportunities to declare the study a success. Such a post hoc rescue recreates the multiplicity problem, and it causes inflation of the study-wise type 1 error rate. Fallback procedure. The next procedure from the family of non-parametric procedures that we're going to discuss is the fallback procedure. If there's any uncertainty around the monotonicity condition, there are other good options to consider, for example, the fallback procedure. This procedure can be thought of as a flexible version of the fixed sequence procedure. It is an extension of the fixed sequence procedure in the sense that it is also derived from the Bonferroni. To define the fallback procedure, we will need to assign non-negative weights to the individual hypotheses in the multiplicity problem that we're considering, and the weights reflect the relative importance of the individual hypothesis. They are denoted by W1 through Wm. Each weight is non-negative, and the weights add up to 1. And of course, if the hypotheses are considered to be equally important, then the weights would be equal, and each weight would be equal to 1 over m. The most important feature of the fallback procedure is that this procedure can continue testing even if there's a non-significant outcome for a certain test in the predefined testing sequence. And this procedure accomplishes this by utilizing the so-called fallback strategy. And that's why it's called the fallback procedure, of course. To be more concrete, I'm going to fix a certain null hypothesis, let's say the hypothesis HI, which is represented by the orange box on the left of this diagram. And this hypothesis will be tested at a certain predefined significance level denoted by alpha I. If the fallback procedure rejects this null hypothesis, which happens if the p-value is less than or equal to alpha I, then this significance level by alpha I equal to alpha I is going to be carried forward to the next hypothesis in the sequence as shown right now in this diagram. This is similar to what we call the investment principle when I introduced the fixed sequence procedure. If a hypothesis is rejected, then its significance level can be applied to the next hypothesis, and in this particular case, the significance level for the next hypothesis, which is hi plus 1, is the significance level which would have been used by the basic Bonferroni procedure. It's alpha times wi plus the significance level that was transferred from hi after that hypothesis was rejected. But what is more interesting when we talk about the fallback procedure is the second option. If the hypothesis hi is not rejected, which is shown by this big blue arrow, the next hypothesis in the sequence can still be tested. It's just it will be tested at a lower level. This is the fallback strategy. Instead of using alpha I plus the Bonferroni level for the next hypothesis in the sequence, the fallback procedure is going to rely on the Bonferroni level, which is equal to alpha times I plus 1. This slide defines the decision rules used in the fallback procedure. In the general case of M null hypothesis, we have defined similar testing algorithms for all of the procedures that we discussed in module C, and then earlier in module D we used a similar format to define the decision rules used in the fixed sequence procedure. And here I would like to make 3 important points. The first one is that testing begins with the first hypothesis in the predefined sequence, which is denoted by H1, And the significance level used in this test is alpha times W1, which is the level that would be used by a weighted version of the bond-forming procedure. Next, when we look at steps 2 through M, we see that a rejection of a certain hypothesis triggers the transfer of the significance level used in that hypothesis test to the next test in the sequence. The fallback procedure continues to reject, and if that happens, the significance levels are going to accumulate quite quickly. For example, if the first m-1 hypotheses are rejected, then the significance level for the very last hypothesis in the sequence is going to be the full alpha. And the last point here is that, as we saw in the diagram on slide 22, if a hypothesis is not rejected, then the significance level for the next hypothesis immediately drops to alpha times Wi, which is again the level that would have been used by a weighted version of the bond-forming procedure. That is the fallback option if the current test happens to be non-significant. The fixed sequence procedure, and that's a fundamental difference between the fixed sequence testing approach and the fallback testing approach, is that the fixed sequence testing procedure does not have such a useful fallback option. Now I'm going to walk you through the individual steps of the fallback testing algorithm using example 4, the type 2 diabetes trial example. Now we're going to use a new set of p-values. This set of p-values will be labeled scenario 3. We again have 3 different dose placebo comparisons and the associated p-values, the one-sided p-values. But in addition to that, before we begin, we need to assign weights to the individual tests. In this particular case, as you see on the slide, the first test receives a 50% weight, and the remaining 50% is divided between the second and third tests. And the greater weight is assigned to dose 1, which is the high dose in this clinical trial example, because it is expected to be more effective than the other 2 doses, based on the historical data or data from previously conducted trials. The diagram on slide 25 provides a visual summary of the underlying decision rules. Here we're looking at all possible outcomes of the tests for the hypothesis H1 and H2, and we can compute the resulting significance levels for the hypothesis H2 and H3. And for example, there's only one option for the hypothesis H1 because it's the first hypothesis, the first test in the sequence. It is always tested at the same level, specifically at alpha times W1. For H2, there are 2 different options. They depend on whether the hypothesis H1 is rejected or accepted. We would need to follow either a solid arrow, which corresponds to the case when the hypothesis is rejected, or the dotted arrow, which corresponds to the case when the hypothesis, the current hypothesis, is not rejected. And you can see here that the significance level for H2 is going to increase compared to H1 if H1 is rejected. And also there are 4 different options for H3. The significance level for the last hypothesis can be alpha, of course, if both H1 and H2 are rejected. This is the best case scenario. And the worst case scenario would be alpha times W3 when the first 2 hypotheses are not rejected, when they are accepted. On this slide and the next 2 slides, we're going to use the familiar plot that shows us the p-values for each one of the null hypotheses in this multiplicity problem. And here we're going to assume the p-values under scenario 3 that were defined 2 slides back. Those p-values are represented here by the 3 orange dots. I would like to point out one more time, since we're dealing with a fixed testing sequence, the hypotheses on the horizontal axis are the actual hypotheses as opposed to the ordered hypotheses that are based on the observed p-values. Testing here begins in step 1 with the first hypothesis in the sequence, H1, and in this particular case, based on the pre-assigned alpha level, which is alpha times W1, and that is equal to alpha over 2. Based on this pre-assigned significance level, the p-value is not significant enough, and therefore the conclusion for step 1 is that the first hypothesis in the sequence is accepted. This is not the end of the game for this fallback procedure, because unlike the fixed sequence procedure, this procedure utilizes a fallback strategy, and this fallback strategy is that if a certain hypothesis is not rejected, then the next one in the sequence will be tested at the pre-assigned level. This pre-assigned level is equal to the alpha times the predefined weight. In this particular case, that predefined weight was 25%, which results in the pre-assigned level of significance level of alpha over 2. And you can see here that the orange dot is slightly below the threshold, which is drawn at alpha over 2, which results in a decision to reject this null hypothesis, and then the significance level used in this test will then be transferred to the next hypothesis in the sequence. And this last hypothesis will be tested in step 3 based on the sum of the pre-assigned level, which is alpha times W3, and the significance level that was carried over from the immediately preceding hypothesis, which was H2. We can verify here quickly that the sum is equal to alpha over 2. The orange dot that corresponds to the p-value associated with H3 is below this resulting threshold of alpha over 2, and therefore the fallback procedure rejects this hypothesis H3 in the last step. And to summarize, the fallback procedure certainly looks more flexible than the rigid fixed sequence procedure. It does, you can see, it tries to adapt to the patterns that it finds in the data. Let us now review the key properties of the fallback procedure. Since the fallback procedure is nonparametric, just like any other nonparametric procedure, it is derived from the Bond-Ferroni, and therefore it would control the family-wise error rate for any joint distribution of hypothesis test statistics. It is a very important property. And the fallback procedure is uniformly more powerful than a weighted version of the Bond-Ferroni procedure, which uses exactly the same weights as the weights that were allocated to the individual hypothesis at the beginning of the testing exercise. But when we compare the fallback to other stepwise multiple testing procedures, for example, procedures with the data-driven testing sequence, there is really no simple relationship between the fallback and those procedures. In some cases, the fallback procedure may be more powerful, for example, or maybe less powerful. For example, it is less powerful than the weighted Holm with the same set of weights, but at the same time, it may be more powerful or less powerful than the weighted Hamel with the same set of weights. As I emphasized a few slides back, the fallback procedure is an extension of the fixed sequence procedure, and in fact we can think of the fallback as a class of multiple testing procedures that are indexed by the vectors of the hypothesis weights. And the fixed sequence procedure is one special case, is one procedure within this class. As you can see on the slide, it corresponds to the case when all of the weight is assigned to the very first hypothesis in the sequence, W1 is equal to 1, and the remaining weights are all set to 0. And it is immediately obvious from this description of the fixed sequence procedure that it represents a very extreme case, that when we put all of our eggs, so to speak, in the very first basket. And as a result, it may be a risky strategy when the monotonicity assumption is violated. When monotonicity cannot be assumed, cannot be justified, the fallback procedure is an attractive, viable alternative to the basic fixed sequence approach. Now, to help us appreciate the advantage of using the more flexible fallback procedure, I'm going to go back to the simulation study that we used to examine the robustness and general operating characteristics of the fixed sequence procedure. And to refresh your memory, I used a clinical study with 3 different endpoints. We assumed that the endpoints followed a trivariate normal distribution and they were equally correlated, so they were indexed using a common correlation coefficient. We're going to assume that the endpoints will be tested sequentially using the fixed sequence procedure and then using the fallback procedure. And when the fallback procedure is applied, then the weights will be assigned as shown on the slide. Half of the total weight is going to be assigned to the first hypothesis, and then 25% and 25% will be assigned to the hypothesis H2 and H3. Here's a summary of the simulation study, and I fully recognize that there's a lot of information in this table, so I'm going to walk you through it. And at first, let's take a look at the second column under the heading Fixed Sequence Procedure. This column shows the probabilities of rejecting the 3 individual null hypotheses. These are marginal powers when the multiplicity adjustment relies on the fixed sequence procedure. This information is exactly what we discussed on slide 17. And the third column under fallback procedure displays the probabilities of rejecting the 3 null hypotheses based on the fallback procedure. Our goals here will be to compare and contrast the results presented in those 2 columns in 3 different cases or under 3 different scenarios that we introduced earlier. And we're also going to differentiate between the cases when the endpoints are independent, when the common correlation coefficient is 0, or when they are moderately to strongly correlated, which means that the common correlation coefficient is 0.5. Case 1, just to remind you, case 1 was defined as the case when all 3 endpoint tests were adequately powered. They were all powered at 80% before a multiplicity adjustment. So now when we apply the fixed sequence procedure, power of the first test is not going to be affected. It will always be 80%, but of course power of the other 2 endpoints is going to drop, and it drops to about 60% or even 50%. When we look by contrast at the performance of the fallback procedure, in the same case, power of the first test is going to be lower than 80%, it's only 70%, but this should not really surprise us. Remember that the fallback procedure spends only half of the available alpha on the first endpoint. The remaining fraction of the alpha is going to be spent on the other 2 endpoints, and this helps improve their power, and it's a very nice improvement. When we compare the second and the third columns under case 1, we see that after the fallback adjustment, the second and third endpoints are powered at more than 70%. Case 2 is almost the least favorable configuration for the fixed sequence procedure. And that is because the first endpoint is underpowered, and this causes a substantial power loss for the second and third endpoint tests. We see that power is extremely low. It drops to 40 and even 30%. But thanks to the fallback option, when we switch to the fallback procedure, we realize that this procedure manages to nicely recover when it comes to the second and third endpoints. If we compare cases 1 and 2, There's very little difference as far as the probabilities of rejecting the second and third hypotheses are concerned. Those numbers are very close to each other. The difference is just a few percentage points. And this is despite the fact that the first endpoint is underpowered. If you remember, under this scenario, when we look at case 2, marginal power for the first endpoint test actually goes down from 80% to 55%. And this shows us how robust the fallback procedure is. The last case, case 3, is a favorable configuration for the fixed sequence procedure because the monotonicity condition is met in this setting. The first endpoint is powered at 95%. And as a result, power of the second and third endpoints declines fairly slowly. The fallback procedure also performs quite well in this case. There is a little bit of power loss for the first endpoint. It drops to 90% from 94%. Once again, because the fallback spends only half of the alpha on this endpoint. And the results for the second and third endpoints are either comparable to the fixed sequence procedure, or sometimes they're even slightly better. So to summarize, when we review those 3 cases that represent either almost the least favorable configuration or sometimes a favorable configuration for the fixed sequence procedure, when we summarize those simulation results, we see that the fallback procedure provides flexibility and more stable performance with a little bit of power loss for the first endpoint compared to the basic fixed sequence procedure. Now I'm going to introduce another class of Bonferroni-based stepwise multiple testing procedures with a pre-specified testing sequence. As I said a few minutes ago, the fallback testing algorithm actually defines a class of procedures, and the fixed sequence procedure is simply a special case of this general class. And now it turns out that we can consider yet another extension, a superset of fallback procedures. We can extend the class of fallback procedures and define a more general class that takes general or arbitrary logical relationships among the null hypotheses of interest into account. This approach enables clinical trial sponsors to build very flexible testing strategies. These testing strategies or testing procedures are known as either graphical procedures or chain procedures. I personally prefer to use the term chain because the underlying testing algorithm is similar to a discrete random process, also known as a chain. For example, we've all heard of Markov chains. From a chain procedures perspective, a multiplicity problem with several hypotheses in a clinical trial is similar to a set of different states for a Markov chain, and therefore chain procedures define rules for transferring alpha from one hypothesis to another hypothesis, and the testing process looks very much like a Markov chain. I will give an example of a chain procedure in a minute, but first let me make a quick comment. Chain procedures, or once again graphical procedures, can be implemented using 2 equivalent testing algorithms. First, cyclical algorithms can be applied, and these algorithms rely on a data-driven testing sequence. But here in this module, I will focus on serial algorithms that assume a predefined hypothesis ordering, and that is simply because in this module we talk about multiplicity problems with a pre-specified testing sequence. I would like to emphasize that the 2 testing algorithms are mathematically equivalent to each other, and they lead to the same set of conclusions and the same set of adjusted p-values. And also, another quick comment is that in what follows, I will provide a rather high-level description of the class of chain or graphical procedures with emphasis placed on its key features. A much more detailed discussion of chain procedures in advanced multiplicity problems, For example, in clinical trials with ordered endpoints, such as the primary endpoints and several secondary endpoints, and lots of additional technical details, a very close look at the underlying testing algorithms. All of this will be provided in the follow-up course, Part 2. To help motivate the general class of chain procedures, to use an example, let's come back to our favorite example again, this example 4, based on a phase 3 trial in patients with type 2 diabetes. In this trial, with 3 dose placebo comparisons, the trial sponsor would like to pursue claims of treatment effectiveness at all 3 doses. And if there is evidence of a beneficial effect in one dosing arm, this will result in a successful trial. So from a regulatory perspective, the 3 dose placebo comparisons are interchangeable. But from the testing perspective, the comparisons may not be equally important. To help the trial sponsor maximize the probability of success in this trial and maximize the market impact of this novel treatment, it will be important to account for the fact that the high dose, for example, which is dose 1 in this case, is more likely to be effective than the other 2 doses. This is the first assumption that we're going to make to build an efficient chain procedure. And then secondly, after a significant treatment effect is established at dose 1, which is once again the high dose, then the other 2 doses, doses 2 and 3, will be tested. And finally, when those doses 2 and 3 are tested, dose 2, which is the medium dose, is more important. It is more promising than dose 3, which is the low dose. All of this information will be taken into account to build a testing algorithm which will be utilized in an efficient chain procedure. Let us see if a testing strategy of this kind can be implemented within the class of fallback procedures. This diagram shows 3 boxes, and they correspond to the 3 null hypotheses of no effect in this clinical trial example. The arrow tells us that the fallback procedure begins with the hypothesis H1, which is the null hypothesis corresponding to the high dose. And after H1 is rejected or not rejected, it will always proceed to H2, which is based on the comparison between the medium dose and placebo. And then after that, it's going to proceed to H3, the hypothesis that relies on the low dose. A very important feature of this fallback procedure is that the null hypotheses are tested sequentially, the first, then the second, and the third, and the underlying algorithm is not flexible enough to support more complex logical relationships. So the logical relationships among the 3 null hypotheses in this clinical trial that we discussed, that we defined on slide 35, cannot be taken into account. For example, we cannot build 2 branches or arrows that would go from the high dose to the medium dose and the low dose. And this is where the more general chain testing approach enters the picture. And what exactly does it bring? It brings flexibility. Most importantly, it brings flexibility. The chain testing approach supports multiple branches. If the trial sponsor needs the most important null hypothesis, which is H1 in this case, to be tested first, followed by the less important null hypothesis H2 and H3, then those logical relationships can be fairly easily taken into account, as we can see on this diagram. The error rate, alpha, will be carried from H1 forward to both H2 and H3, and you can see that if you follow the solid arrows that connect the box on the top to the 2 boxes at the bottom of this diagram. And secondly, when we focus on H2 and H3, we said a minute ago that H2 is more important from the sponsor's perspective. It should be tested first, followed by H3, and therefore the important message here is that the chain testing approach enables clinical trial sponsors to build flexible multiple testing procedures that are customized, that are tailored to the objectives of each individual clinical trial. What we saw on slide 37 was a general outline of the chain testing strategy, and on the next several slides I will give a more formal definition of the underlying testing algorithm. The two key components of any chain procedure are the rules known as the alpha allocation and alpha propagation rules. First, when we look at an alpha allocation rule, this is the rule that defines the initial distribution of the error rate, which is alpha, for example, a one-sided alpha of 0.025, across the hypothesis in a given multiplicity problem. This rule governs the process of splitting the overall alpha over the hypothesis to be tested. And the second rule, which is the alpha propagation rule, defines the process of transferring or propagating the error rate from a rejected hypothesis to other non-rejected hypotheses. These are, of course, somewhat formal definitions, and these rules will be illustrated on the next several slides. But I would like to point out that thanks to these rules, a chain procedure can adapt to a very broad class of multiplicity problems and can support very flexible decision rules. When we apply the alpha allocation rule, we simply assign the initial alpha levels to the three null hypotheses in our multiplicity problem. As you can see on this diagram, those hypotheses are represented by the three orange boxes, and within each box we see the hypothesis label and also the initial alpha level or significance level at which it will be tested by the chain procedure. Specifically, the significance level assigned to H1 is equal to alpha times W1. For H2, it's alpha times W2. And finally, for H3, it's alpha times W3. This aspect of any chain procedure is exactly the same as the process of allocating initial significance levels for a fallback procedure, and it's exactly the same type of allocation scheme which would have been used in a weighted bond-throwing procedure. The second step, and that's a very important component of any efficient chain procedure, the second step here is to specify the alpha propagation rules. Those rules are specified by the weights that are assigned to the connections, to the arrows. For example, in this case, it's alpha 1 times G12, alpha 1 times G13, and then finally at the bottom, alpha 2 times G23. What exactly are those numbers? These are the fractions of the alpha that would be carried forward after the rejection of the corresponding hypothesis. For example, if there's a significant treatment effect at the high dose, which is dose 1, and the hypothesis H1 is rejected, the orange box, I'm referring to the orange box at the top of this diagram, then a certain fraction of that significance level, alpha 1, specifically alpha 1 times G12, will be carried forward to the hypothesis H2, and then the rest of it, which is alpha 1 times G13, will be carried forward to the hypothesis H3. With this basic background information in place, let us now formally define the parameters of the chain procedure from slide 39. First of all, the hypothesis weights W1, W2, and W3. These are the values that reflect the relative importance, initial relative importance of the three hypotheses. These are non-negative values that add up to 1. Secondly, we have the transition parameters that are denoted by G12, G13, and then G23. These transition parameters are really the secret ingredient of efficient chain procedures, as I emphasized on slide 39. By using these parameters, we can custom build a chain procedure which is fully aligned with the predefined logical relationships. Each transition parameter defines the proportion of alpha carried forward from one rejected hypothesis to another hypothesis. In this particular trial, as you see at the bottom of the slide, G12 is the fraction of alpha 1 carried forward from H1 to H2, provided H1 is rejected. And similarly, when we look at G13 and G23, these are the fractions of the corresponding significance levels that are carried from H1 to H3 and from H to H3, provided in this case that H1 or H2 are rejected respectively. The conditions that we impose on those transition parameters is that, of course, they're all non-negative, and in addition, G12 plus G13 is going to be 1, because all alpha is going to be transferred from H1 to H2 and H3 if H1 is rejected. This diagram is somewhat similar to the diagram that we built for the fallback procedure in the same clinical trial example, and it summarizes the decision rules used by the chain procedure. This diagram defines the significance levels for each hypothesis in the sequence as a function of the test outcomes earlier in the sequence. I think it's a nice visual way to summarize those complex decision rules. For example, we can see here immediately that if we look at the solid arrow, it represents the case when H1 is rejected, and thus the significance level for H2 would be given by this formula. It's a rather complicated formula, but simply reflects the predefined alpha propagation rule. This significance level is the sum of the initial alpha level, which is alpha times W2, plus the contribution from H1 after H1 is rejected. This term was transferred from H1, and the same applies to the other cases in this diagram. We are now ready for a numerical example. This table shows us a set of treatment effect p-values in the type 2 diabetes trial. It's yet another set of one-sided p-values that we have not explored before. We will label it scenario 4. These are the, in addition to the one-sided p-values, we're also going to specify the initial weights assigned to those 3 dose placebo tests. For simplicity, it doesn't have to be done this way, but just simply for simplicity, for the sake of illustration, we're going to assume that the 3 dose placebo tests are assumed to be equally weighted, and therefore they're equally important. And then at the bottom we see the transition parameters for this chain procedure. We're going to assume that G12 is equal to 1/2, G13 is equal to 1/2, and finally G23 is equal to 1. That means that after we reject the null hypothesis of no effect at the high dose, which is dose 1, then the resulting significance level is going to be split equally between the hypothesis of H2 and H3. And finally, G23 is equal to 1 simply because all alpha will be transferred from dose 2 to dose 3 after a significant effect at dose 2 is established. We're going to now take a look at a familiar set of plots that show us the relationship among the one-sided p-values across the 3 hypotheses of interest, and we're going to apply a 3-step testing algorithm for the chain procedure that was defined on slide 42. We're going to begin with step 1, and in step 1, the hypothesis H1 is going to be tested at the predefined alpha level. In this case, this alpha level is alpha times W1, which is equal to alpha over 3. And we can see from this plot that the orange dot that corresponds to the p-value for H1 is below the threshold that was drawn at alpha over 3. That means that this hypothesis is rejected. There's evidence of a beneficial treatment effect at dose 1. And in addition to this rejection decision, we're going to also define the fractions of the alpha that will be transferred to the hypothesis H2 and H3 Those fractions are derived based on the predefined transition parameters, and the specific formulas are shown on the slide. Half of the alpha will be carried over to H2, and the other half will be carried over to H3. As a result, when we now take a look at step 2, in step 2 the hypothesis H2 will be tested, and in this case the corresponding significance level, which was updated after the rejection of H1, this updated significance level is alpha over 2. It is higher than the original predefined significance level for H2. However, despite this updated significance level, the p-value for H2 is simply very, very high. And as a result, the hypothesis H2 cannot be rejected. It is accepted, and therefore no additional alpha will be transferred from H2 to H3 according to the pre-specified alpha propagation rule. This means that in step 3, the hypothesis H3 will be tested again at the level alpha over 2. We can compute that level by following the formula presented at the bottom of the slide. The p-value for that hypothesis is significant at that level, and therefore we conclude now that the hypothesis H3 is in fact rejected by this chain procedure. Before we wrap up this section, I would like to present a set of decision rules for a general chain procedure in a general multiplicity problem with m null hypothesis. First, we need to define the hypothesis weights. Those initial hypothesis weights are denoted by W1 through Wm. Secondly, we're going to define a set of transition parameters. It is actually a matrix of transition parameters because those transition parameters are indexed by two indices, I and j. So the transition parameter Gij, as you see on the slide, represents the fraction of alpha I, which was a significance level used in testing the hypothesis Hi. So this is the fraction that will be carried over from Hi to Hj after Hi is rejected. The corresponding alpha propagation rule is defined at the bottom of the slide, and it states here, as you can see, that whenever the chain procedure rejects a null hypothesis, for example, when it rejects the hypothesis Hi, then the significance level used in that test is going to be distributed among the remaining null hypotheses, and this contribution to Hj is going to be proportional to the predefined transition parameter Gij. The resulting class of chain procedures is extremely flexible, and it can be used to construct multiple testing strategies that reflect complex relationships among objectives, clinical objectives in a clinical trial. This slide summarizes key properties of chain procedures, and I will begin with the statement at the bottom. Since the class of chain procedures serves as an extension of the class of fallback procedures, specifically chain procedures are derived also from the bond-forming procedure, the key properties are exactly the same as what we discussed in the context of fallback procedures. First, chain procedures control the family-wise error rate for any joint distribution of hypothesis test statistics. And secondly, chain procedures are uniformly more powerful than weighted versions of the bond-forming procedure, with the same set of hypothesis weights, and at the same time, chain procedures may be more powerful or sometimes may be less powerful than weighted Holm procedures. Again, those procedures must be constructed with the same set of weights. This last slide before the discussion of software implementation summarizes the key points for modules C and D. It includes all stepwise multiple testing procedures that we have discussed. That includes procedures with a data-driven and pre-specified testing sequences. And it's actually very similar on a similar slide that are presented at the very end of module C. First of all, we can see here 4 procedures at the top that are arranged in the order of increasing power. The bond-forming procedure is on the left-hand side. It is uniformly less powerful than the other 3 procedures. And the Hobble procedure is placed at the right-hand side because it is uniformly more powerful than the other 3 procedures. And now I'm going to add the fallback and chain procedures in a separate box at the bottom of this diagram. And this box shows that the fallback/chain procedures are clearly better than the basic bond-forming procedure. They're generally comparable to the Holm procedure, Hogberg, and Hummel procedures, in the sense that sometimes they can provide a power advantage over the Hogberg and bond-forming, or sometimes they could be less powerful than the Hogberg and Hummel procedures. And this is why the box representing the fallback chain procedures is shifted slightly to the right. These procedures are in the same league as powerful stepwise procedures that we introduced in Module C. Software implementation section. And now we are ready to talk about software implementation of the stepwise procedures with a pre-specified testing sequence, specifically the fixed sequence, fallback, and general chain procedures. I would like to begin by saying that as of this time in SAS version 9.4, these procedures are not supported by standard SAS stat procedures, but there are 2 macros that were written by me to support these popular multiple testing procedures. First, the pval-proc macro, which I introduced in Module C. It also supports the fallback and fixed sequence procedures. And there's also a standalone macro, chain server macro, which implements general serial chain procedures, for example, chain procedures with a pre-specified testing sequence. The fixed sequence, fallback, and general chain procedures can also be implemented in R using the Mediana package. The adjusted p-values function supports these stepwise procedures, and I will provide multiple examples later in this module. We're going to use the following set of one-sided p-values based on the individual dose-placebo comparisons from example 4, which is again based on the type 2 diabetes trial. This particular set of p-values was introduced earlier and was labeled scenario 4. In addition to those numerical values, I'm going to point out that we assume for simplicity that the individual comparisons or the individual hypotheses in this multiplicity problem are assumed to be equally important, and therefore the hypothesis-specific weights are all set to 1/3. As in Module C, if we would like to invoke the pval-proc macro, we need to set up a data set with the raw p-value for each hypothesis and the hypothesis-specific weights. Once again, we assume here that the hypotheses are equally weighted, and therefore the input data set called EX4 is defined as shown on the slide. This data set, EX4, is passed to the pval-proc macro. We call this macro. It produces a data set with multiplicity adjusted p-values, ADJP, and then we can print the resulting adjusted p-values. I would like to add that the data set also contains multiplicity adjusted p-values based on the fixed sequence procedure, and the variable name that we would need to use if we were interested in the fixed sequence procedure is shown at the bottom of the slide. But now we're going to focus on fallback adjusted p-values, and the output produced by the pval-proc macro is displayed on slide 55. We see as before a set of one-sided raw p-values and associated fallback adjusted p-values. If we apply a one-sided alpha of 0.025, It's easy to see that after the fallback-based multiplicity adjustment, only the first adjusted p-value is significant, and we can conclude that a statistically significant effect is present only at dose 1 in this type 2 diabetes trial. Now, to implement general chain procedures, we will need to formally define two key elements of any chain procedure. It is the vector of hypothesis weights, which is specified by the alpha allocation rule, and it's the matrix of transition parameters. The transition parameters, as you remember, are specified by the alpha propagation rule, and as we said earlier in this module, each transition parameter in this matrix defines the proportion of alpha, which will be carried forward from one hypothesis to another hypothesis after this first hypothesis is rejected. For example, in the type 2 diabetes trial, we assume that the hypotheses are equally weighted, and as a result, the elements of this first vector, denoted by W, are all equal to 1/3, and the matrix of transition parameters is defined as follows. Let's select, for the sake of example, the second element in the first row. This element is equal to 0.5, and that means that after the first hypothesis in this multiplicity problem is rejected, and it's the first hypothesis because we're looking at the first row in this matrix, then half of the significance level used in that test will be allocated to the second hypothesis because we're looking at the second column here, and the remaining 1/2 will be allocated to the third hypothesis in this multiplicity problem. Now that we have defined the vector of hypothesis weights and the transition matrix, it is quite straightforward to create a data set. It's called EX4 chain that contains the raw p-values. It also contains the predefined hypothesis weights and the predefined transition parameters. You can see the code for setting up this data set on this slide. And the next step is to pass this data set to the chainsir macro. After we call this macro, it produces a data set with adjusted p-values. And the output of this macro is shown on slide 59. As before, we see here a column of the raw p-values as well as the multiplicity adjusted p-values based on this particular chain procedure. And we also see that with this chain procedure, two null hypotheses can be rejected at a one-sided alpha of 0.025, and we can specifically claim a significant effect at dose 1 and dose 3. And it is useful to remember that with the same set of p-values, when we apply the fallback procedure a few slides back, then the fallback procedure was able to reject only one null hypothesis. We're now going to switch from SAS implementation issues to R implementation issues, and we will begin with the implementation of the fallback procedure. We will use the adjust p-values function from the Mediana package. And this function treats the fallback procedure as a special case of chain procedures. As a result, to compute adjusted p-values based on the fallback procedure, in example 4, we will need to define the vector of hypothesis weights. It is denoted by W on the slide, and also the matrix of transition parameters denoted by G. The weights and transition parameters for example 4 are defined on this slide. As you may remember from Module C, to call the adjust p-values function, there are two required objects. The first one is raw p, it's the vector of raw p-values. And secondly, the second parameter, proc, defines the multiple testing procedure. In this case, it is set to chain adjust to implement a multiplicity adjustment based on a general chain procedure. The last parameter, par, is an optional parameter. This parameter defines other parameters that may be required by specific multiple testing procedures. In this particular case, this optional parameter is actually a list, and it includes the vector of hypothesis weights and the matrix of transition parameters for this fallback procedure that we defined on slide 60. This slide shows the adjusted p-values based on the fallback procedure. You can easily verify that this set of multiplicity adjusted p-values is identical to the adjusted p-values that we presented on slide 55. And we can call the same function adjust p-values to compute adjusted p-values using the chain procedure. This chain procedure is derived using the vector of hypothesis weights and the matrix of transition parameters that we defined back on slide 56. We just need to define these two objects and then pass them to the adjust p-values function along with the vector of raw p-values, and the adjust p-values function computes, as before, a vector of chain adjusted p-values. These adjusted p-values are shown on slide 64, and they are identical to the p-values that I presented on slide 59. Those p-values were computed using a SAS macro.